So continuing on with some questions that are inspired by the successes we already had, we want to think about what about instead of just this differential equation, which is second order, what if we had an equation like still constant coefficients like a times the fourth derivative of y plus b times the third derivative plus c times the second derivative plus d times the first derivative plus e times y equals 0. Can we get solutions to that in the same way as we did, in the same very simple way as we did with the second order equation, given that we had complex numbers to work with? So the guess, of course, is just e to the alpha t. And what's going to have to be true? Well, we could plug that in. So we're going to get e, and then when we take four derivatives, we're going to get alpha to the fourth, e to the alpha t, plus b, three derivatives, chain rule is going to be activated 3 times, alpha cubed e to the alpha t, plus c alpha squared e to the alpha t. You'll notice I'm back to the whiteboard, but I've got a new computer, new microphone. Let me know if the sound seems a little bit weak to me. Oh, sorry, using e twice, but let's not worry about that too much. So make a comment if the sound is really painfully bad. So, just as in the other case with the second order, we come down to a polynomial equation that needs to be solved for alpha. Where, in other words, we've got now here a fourth degree polynomial that we need to have a root for. In fact, how many roots would we like? We want 4 roots. Okay. Now, that does become an issue, just like the thing I skipped with the second order equation. If the roots coincide, if we have higher multiplicity roots, not simple roots, then there is more to be done. But if we have 4 distinct roots to this polynomial, a alpha to the fourth plus b alpha cubed plus c alpha squared plus d alpha plus e equals 0, then we're going to be good. And that's exactly what the fundamental theorem of algebra is saying, that we're going to have at least one root, and generally, most of the time, we're going to have 4 distinct roots. And it turns out, and again, this is the part I don't want to concentrate on right now, is that if the roots aren't distinct, you can make it work. And you certainly don't have to invent new kinds of numbers just because of that special case. Okay, so this is really nice. The link between the algebra and the calculus is very tight. And it tells us that, in fact, for any degree equation, we're going to have a procedure that that gives us solutions to any linear, constant coefficient, ordinary differential equation, no matter how high the order. Now, the FTA doesn't guarantee that those roots are going to be simple to express in terms of like square roots, cube roots, things like that. There's some very powerful big theorems about how complicated those answers can be, but they will be there, and maybe you can approximate them numerically, even if you don't have a really nice closed form for them. So that's just a nice parallel between the algebra and the calculus, the analysis. Now, a third point I want to make is another calculus fact, and I'm going to be pretty brief about this. But it's that if you have lots of physical systems, don't just have one dependent variable. Often you have a whole vector worth of quantities that can vary in time. Let's say y1 through yn. So these are all functions of t. So I could put in the explicit t dependence everywhere. And so I've got a vector valued function. And you can think of that, the lowest tech way to think of that is just a bunch of quantities you need to keep track of. Like, here's the current in one loop, here's the current in another loop, here's the voltage at this one location, here's a voltage in another location in a circuit. Or you've got some sort of mechanical truss, and these are the positions of all the nodes, the junction points in the mechanical truss, like a bridge or something like that. It's a very reasonable thing to need to do. And if we're lucky enough that that satisfies a linear differential equation, a linear constant coefficient homogeneous differential equation, to be precise, then what you have, the way you write that, is just y prime is a matrix A times y. And here A is a matrix of constants. In more complicated situation, this could be a variable, it could be a function of t, but that's not what I want to focus on. So, and it turns out this is a very natural generalization of the previous case, where we had a higher order equation in one variable. Those can actually be modified to be rewritten as a first order equation in more than one variable. It's a very standard technique in differential equations. So, another way to say this again, low tech, is just y1 prime is some combination, some linear combination of y1 through yn, and y2 prime is some linear combination of y1 through yn. It's just a system of differential equations where the rate of change of each of these quantities can depend on not only itself, but all the other quantities. Okay, and the guess here is very closely related to what we had before. It's simply that y of t, now that has two ways of being complicated. It is a function and it is a vector. And you just separate out those two pieces. You say, instead of like constant times e to the alpha t, with that constant just being a number, you guess that maybe there's a constant vector. And I'm going to use lambda because at this point, I've been kind of waffling between whether lambda or alpha is a good letter, but at this point, lambda actually is totally the right letter for this. It's a very standard letter for this case. That we've got a constant vector. So that incorporates the complexity of the algebra and the vector nature of it. And then this is a scalar function, so it doesn't have any vector nature, but it does have the variability to it. So this encodes the variability in t, this encodes the vector nature of it. Turns out this guess is exactly the analog of what we were doing. And I'm just going to say, because I just, in this appendix, I don't want to open up a whole new chapter in differential equations. Turns out here's what needs to be true for this to work. When you plug it into this equation, try it. It's not super hard. You need a purely algebraic fact about how v and lambda relate to each other, that AV equals lambda v, so that when you put the vector v into A, it doesn't change direction. All it can do is scale, and it has to scale by exactly that number. And there's one really important proviso. If you think about this and you think special cases, think like a mathematician, think about special, stupid, degenerate cases. This always works for v equals 0. But is this possibly interesting when v equals 0? Well, no. This is a linear homogeneous equation. Y of t equals 0 is, of course, a solution to this, but it's not interesting. There's no behavior. And so we require that v is not equal to 0. Now, it turns out the next stage in the standard story here is it's not too hard to show, if we know a little bit of linear algebra, is that if you take lambda times the identity matrix, subtract it from A, and take the determinant, that has to be 0 for this to work. That's basically, it's a necessary condition for this to happen. And what is this? This is like 3 minus lambda, 2 minus 1, 2 minus lambda, minus 5, 5, 7, 4 minus lambda. You take the determinant of that. That's going to be a polynomial in, let's see, it's going to start out with a minus lambda cubed. When you actually expand that out, it's going to be in this case, because it's a 3 by 3 matrix, it's going to be a cubic polynomial in lambda. And in general, this is a polynomial equation, because A has fixed numerical coefficients in a particular problem. This is a polynomial equation in the real number lambda. Oh, wait, the real number? Most of the time, or a lot of the time, you're not going to get solutions unless you allow complex numbers for lambda, but that's the least surprising thing I've said, hopefully. That you need lambdas to be complex for this to work. I could have actually started with this, and this is a very powerful place to start, but it's a more sophisticated place to start because we have to know a little of linear algebra. That this idea really requires lambda to be able to be complex if you have any hope of a general solution procedure that will work for all matrices. Again, there's a similar issue about sometimes you'll get multiple solutions to this, multiple roots, and that gets more complicated algebraically in terms of the matrix stuff, but it doesn't require new numbers. Let me give you the terminology here. In this situation, well, yeah, like right here, either way. The v is called an eigenvector, and then the lambda is called the corresponding eigenvalue. And so you can look up about eigenvalue singular, eigenvalues and eigenvectors. And the punchline is that to do eigenvalues and eigenvectors, which are incredibly important in linear algebra, in dynamics, and differential equations, just a hugely basic concept, you're going to need complex numbers because you need the fundamental theorem of algebra. Okay, so I'll talk about a few other extensions that this goes in that are a little less obvious in the next video.